So we will continue our chapter 4 review, and we were arrived at question 4. Question 4 is asking, both atomic elements and molecular elements exist. Are there such entities as atomic compound and molecular compound? If so, provide an example and microscopic drawing. If not, explain why not. So I want to remind you that the question 3 here was asking for the 7 elements that are diatomic molecules, and that's what we call molecular elements. So let's give examples of molecular elements. Molecular elements would be, for example, Br2, Cl2, etc. There is also, for example, sulfur 8. So let me put these 2s as subscripts. So these are examples of molecular elements. They are elements because they are made of only one type of atom, but they are molecular because they are made of more than one atom bonded together. So 2 atoms of bromine together, 2 atoms of chlorine together, or 8 atoms of sulfur together. So that's why we call them molecular element. And then the atomic elements are, all the ones you see on the periodic table, like carbon, copper, iron, silver, all these elements that when you talk about them, it's just their single element, as you see it in the periodic table. So these are the atomic elements. So what is a compound? And let me copy this. So a compound is made of 2 or more elements bonded together and functioning as a unit. So atomic compounds are not possible, but molecular compounds are, like, for example, H2O, CO2. So a compound needs to have 2 atoms of different kind bonded together. That's, 2 or more elements bonded together. And for a molecular compound, you need 2 non-metals. You will learn that in chapter 4, that the periodic table, and let me show the periodic table here. There is a classification, and that uses this staircase here that you see to the right, that goes down from boron to polonium. And this staircase is very useful to help you see the metals. Metals are all the elements that are on the left side of this staircase. And then the non-metals are the elements on the right side, in the upper right corner of the periodic table. So it's all the carbon, nitrogen, oxygen, fluorine, sulfur, bromine, iodine, etc. These are what we call non-metals. And so when you have non-metals bonding together, we call them a molecular compound. So these are examples of molecular compound because they are made of non-metals only. And so atomic compounds are not possible. You cannot have just one type of element, and then it would be a molecular element otherwise, right? So that's why atomic compounds are not possible. So we'll continue with question 5. Identify the following elements. So you have clues. The first one, A, the halogen in period 5. So for this, you need a periodic table. I like to use this version of the periodic table because it has the group numbers with the letters below the group numbers that go from 1 to 18, from left to right. But this one also has the group numbers. So remember how group numbers are columns, right? And periods are the rows. So this table has the group numbers with the letters A and B. So that's why I like this one. So we are looking for the halogen in period 5. So period 5 means, if I highlight it here, it's this period, right? The periods are rows, so row number 5 here. And we said the halogen. So you need to know what are the halogens. And so the halogens are group 7A here. So fluorine, chlorine, bromine, iodine, maybe astatine, these are considered the halogens, right? And so if you look at period 5, then the halogen is iodine. So here you will want to type iodine, I. Now we're looking for the metalloid in group 3A. Metalloid in group 3A. So I told you about metals versus non-metals that are distinguished by the staircase. And so the metals are on the left side, the non-metals are on the right side. But anything that is, underlined can be considered a metalloid. But be careful, there are exceptions. So boron is a metalloid, silicon, germanium. Be careful, aluminum is not metalloid, it's a metal. Arsenic is a metalloid, antimony, tellurium, and then you go to astatine. Polonium is not a metalloid. Polonium is also a metal. Okay, so there is boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. And that's 1, 2, 3, 4, 5, 6, 7 metalloids only. And here we are looking for the metalloid in group 3A. So groups are the columns. And here metalloid in group 3A. So 3A is boron. So that's the metalloid in group 3A with symbol B. Now we're looking for the metal in group 6A. Metal in group 6A. So metals are on the left side of the staircase. And 6A. So 6A is this group here, So you go down until you find the metals, because oxygen, sulfur, and selenium are non-metals. Tellurium is a metalloid, and then polonium is a metal. It's not a metalloid, even though it touches the staircase. It's still considered a metal. So the metal in group 6A is polonium with symbol PO. Let me put this in another color here so we see what I've done. Okay, now we are looking for the non-metal in group 4A. Non-metal in group 4A. So group 4A is here. It's the group of carbon, silicon, germanium, tin, lead, etc. And we are looking for the non-metal. So we have to stay above the staircase. And group 4A, here there is only carbon, because silicon then is a metalloid, germanium is a metalloid, tin and lead are metals. So the only non-metal in group 4A is carbon with symbol C. Now we are looking for the non-metal in group 1A. So group 1A is here. That's the group where you have hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. This is called the alkali metal, except that hydrogen is an exception. It's not an alkali metal. Hydrogen is the non-metal that is part of group 1A. And that's an exception. All the others are metals except for hydrogen. So hydrogen. The alkali metal in period 4. So we said the alkali metals are all these, from lithium going down to francium. These are called the alkali metal. And we are looking for the one in period 4. So period 4 means, the fourth row. And so that's potassium. potassium. And here potassium, be careful, the symbol is K. It's not intuitively related to its name. Now the alkaline earth metal in period 2. So where are the alkaline earth metal? The alkaline earth metal are just next to the alkali metal, and that's the metals in group 2A. We call them alkaline earth metals. And we are looking for the one in period 2. So period 2 means beryllium here. Row 2 is beryllium. Beryllium with 2 L's. And so that's the alkaline metal in earth in period 2. Alkaline earth metal in period 2, sorry. Now we're looking for the noble gas with 2 electrons. So where are the noble gases? That's another name you need to know, and that's the noble gases are group 8A. It's helium, neon, argon, krypton, xenon, radon, and oganesson. These are all noble gases, which means they are gases, and noble means they are inert. It means they are very stable and non-reactive. And so they are very particular for that. And you will see that we will refer to the noble gas a lot. So you need to know where they are and which elements they are. And here we're looking for the one with 2 electrons. So the atomic number, which is the number that you see above the symbol here, atomic number, tells you the number of protons in the nucleus and the number of electrons if it's the neutral element. And here, helium is having an atomic number 2, which means it has 2 protons in its nucleus and 2 electrons when it's the neutral, atom, helium. So that's helium here with symbol He. Next, the only metal liquid at room temperature, only metal liquid at room temperature. So we need to look into the left side of the periodic table where metals are. And all metals are solid, metallic, shiny, heavy most of the time. And the only metal is actually mercury. So this is not shown in my periodic table here, but some periodic tables show the physical state with colors, for example. And the only liquid metal at room temperature is mercury. You see mercury being used in barometers. And so it looks like it's a shiny silver. And it's very heavy. It has a density of about 13 grams per milliliter, which makes it quite dense. The only non-metal liquid at room temperature. So this time we need to look at non-metals that are liquid at room temperature. So non-metals are on the right side of the periodic table. So, carbon, nitrogen, sulfur, bromine, all of that. And so as we said about the noble gases here, the noble gases are all gases. Fluorine, chlorine are gases. Oxygen, nitrogen are gases. Boron, well, that's a metalloid. Carbon, phosphorus, sulfur, selenium, iodine, astatine are all non-metals that are solid. The only one that is liquid is bromine. Bromine is the only non-metal liquid. It's a brown liquid with a stench. It doesn't smell good. So bromine is the one. Transition metals with a single letter symbol. Okay, we need to define what are transition metals. Transition metals are those found in the B groups. So it's all of these. What I have in red here, it's all the metals in the B group. If you look at the group number, there is a letter capital B next to the number. And so that's what we call the B groups or the transition metals, and also the D block you will see as you learn with chapter 11. We also call that the D block. And so that's where are the transition metals. And so among them, we need to find the one that have a single letter symbol. Single letter symbol. And there is vanadium here and yttrium there. Sorry. Let me select yttrium. No. Oh. Okay. Yttrium. That's the only. Oh, well, there is also tungsten. Tungsten here. There is 3 of them. Vanadium, yttrium, and tungsten. So let's write them. Vanadium with letter V. Tungsten, W. And then yttrium with the letter Y. So that's the 3 transition metals with a single letter as a symbol. The inner transition metal with a single letter symbol. So where are the inner transition metals? That's another name for a group of metals. And they are, let me move this if I can here. Okay, the inner transition metals are here. It's the 2 rows at the bottom of the periodic table that are taken from period 6 and 7. If you look at this black thing here, it shows you how they actually belong to period 6 and 7. And if you were putting them these 2 rows there, you would have to widen the periodic table and make it very wide. And that's not convenient. So that's why very often those 2 rows in the middle here are put down below the table. And these are called inner transition metals. And we are looking for the single letter symbols. So here, single letter symbols. There is a uranium. And that's the only one. Uranium. Uranium with letter U. And then all other elements with a single letter symbol. So we already have the vanadium, tungsten, yttrium, uranium. So we need all the others. So in group 1A, we have the hydrogen and the potassium. So let's write this: hydrogen, potassium with K. Let's look at, so we already collected the one from the transition metal and from the inner transition metal. So now let's look at the non-metals. We have boron, carbon, nitrogen, oxygen, phosphorus, and sulfur, and iodine. So all of these. Boron with capital B. Carbon, capital C. Nitrogen, capital N. Fluorine, capital F. Phosphorus, capital P. Sulfur, S. Iodine, I. So boron, carbon, nitrogen, fluorine, phosphorus, sulfur, iodine. I think I have them all. So that's answering that question. So we need to do question 6 now and complete the following table for isotopes. So isotopes, by definitions, are iso means same. Tops comes from topos, which means place in Greek. So isotopes means, element, atoms you find in the same place on the periodic table. And so, for example, carbon has several isotopes. And what differentiates the isotopes of carbon is the mass. They have different masses. They have the same number of protons, and that's what identifies them. Same number of electrons if they are neutral. And what makes them different is the number of neutrons. And because neutrons have a mass of 1 atomic mass unit, this will change the mass of the atom. And so we use those symbols of using the symbol element. And then on the upper left corner, we write the mass number, which is symbolized by capital A. And on the lower left corner, we write the atomic number, which is symbolized by Z, capital Z. And so here you have Hg, that's mercury, and there is 202 in the upper left corner, and then 80 in the lower right corner. And so the top number is the mass number. So here you can complete the table by writing 202 for the mass number. And then we said the bottom number is the atomic number, Z. So then you can write 80 here. And you can confirm with the periodic table that mercury is indeed atomic number 80, right? It's the number above the symbol. And so the atomic number represents the number of protons. That's by definition. So that means we have 80 protons. And because this is neutral, there is no charge, then we can also say there is 80 electrons. It's neutral because you have 80 protons, so 80 positive charges cancelled by 80 negative charges from the electrons. Now, to find the number of neutrons, you do the mass number minus the number of protons, because the mass number represents the number of protons plus the number of neutrons. So if you do the mass number minus the atomic number, you get the number of neutrons, and that's, let me just make sure I have the right value, 122. So that's going to be 122 here. 202 minus 80. And the name, that's mercury. We've done the first one, so let's do cobalt now. We have the name, so let's find cobalt in the periodic table. Cobalt is here. It's a transition metal in group 8b. The symbol is capital C, lowercase o. So let's have this symbol. Let me insert an equation here, actually. So capital C, O. So from the periodic table, you can determine the atomic number, right? So let's look at cobalt. The atomic number is the number above the symbol, and that's 27. So here you can write 27. By definition, the atomic number is the number of protons, so we can write number of protons 27. Here it doesn't say that it's an ion, so we also have 27 electrons. For the number of neutrons, you need to use the mass number that is given here, so 59. So 59 minus the number of protons, 27, equals 59 minus 27 is 32. So that's the number of neutrons for this isotope of cobalt. So now we can finish the symbol of the isotope and put the mass number on the upper right. So let me use this. Okay, so CO. So in the upper left corner, you place the mass number, and here it's 59. And on the lower left corner, you type the atomic number, and that's 27. And there you go. That's the isotope for this cobalt isotope. That's the symbol I mean. Okay, let's do row number 3. We are given the atomic number and the mass number. Atomic number 10. So given that, you go to the periodic table and look for atomic number 10. Atomic number 10 is neon. So that's neon, the name. That's the symbol neon. So let me insert an equation first. And this. So neon. Okay. The atomic number is also the number of protons. So you can write 10 protons here. And it's nothing indicates that it's an ion. So it's also 10 electrons. Now to find the number of neutrons, we do the mass number, which is 20 here. It's given minus 10 protons equals 10 neutrons. So this neon isotope has exactly 10 protons, 10 neutrons, and 10 electrons. So let's finish the symbol here. Neon, so atomic number is 10, so we can put that in the lower left corner. And then in the upper left corner, we write the mass number, and that's 20. And that's the symbol for the isotope of neon with these numbers. Next, we have titanium. Well, I shouldn't say that, it's Ti. So let's look for Ti in the periodic table. Ti is here, and that's titanium, as I said, with atomic number 22. So we have the name, we have the symbol, we have the atomic number. So titanium 2 plus, you know, it's an ion, 2 plus. Atomic number 22, and that was also given here, right? Remember how the lower number is the atomic number. The atomic number is also the number of protons, so we can write 22 protons. However, here it's not neutral, it's a 2 plus ion. And you know that atoms, they become ions by gaining or losing electrons, right? That's the only thing that you can take out or remove from the atoms. You cannot change their number of protons because then it would be a different element. So Ti is still 22 protons, but now we have 2 positive charges. That comes from 2 protons in excess compared to the number of electrons. So that means you have 2 protons in excess compared to the number of electrons. So you want 22 minus 2, and that's going to be 20 electrons. So that's how you can find out the number of electrons. Because 20 electrons with negative charges will cancel 20 protons, you know, 20 positive charges, and there will be 2 positive charges in excess, and they will show up here on the ion. For the mass number, we can find it here. It's the upper number. So 46 is the mass number. And then the number of neutrons is the mass number minus the atomic number. And that's 46 minus 22, 24 neutrons for that as an isotope of titanium 2 plus. So let's do the last row here. We have the atomic number, the number of neutrons, and the number of electrons. So let's find what element this is. Atomic number 20. Atomic number 20. Here it's calcium. Calcium, atomic number 20. Calcium. It's going to be Ca, the symbol. The atomic number here can be written in the lower left corner. So let's find out the number of protons here. We have 20 protons because the atomic number is 20. Because we have 20 protons and 20 electrons, we add them together to get the number, the mass number. So the mass number is 40. So then we can have the 40 on top here. So this was actually in blue. Okay, not given. You have to pay attention to the fact that the number of protons is not the same as the number of electrons. We have 20 protons, so 20 positive charges and only 18 negative charges. So there is 2 positive charges in excess. So this is actually an ion. So I need to add the charge in the upper right corner here. And because we have, 20 positive charges minus 18 negative charges, that's 2 positive charges in excess. And that's going to be a 2+ ion. So it's calcium 2+. And that's it. So we arrived at question 7. List all predictable ions that are isoelectronic to argon. So there's a lot in that question here. First, let's define what it means to be isoelectronic to argon. So argon, if we look at the periodic table, it's a noble gas here, atomic number 18, right? So to be isoelectronic to argon means to have the same number of electrons, because isoelectronic means having the same number of electrons as argon. And here, argon has 18 electrons, because if you look at the periodic table, it's still showing up here on the right. Argon has atomic number 18, which means it has 18 protons in its nucleus. And as the neutral atom, it has 18 electrons. 18 protons, 18 electrons, right? So to be isoelectronic to argon means having 18 electrons like argon. And so all the other elements, for them to be isoelectronic to argon, they have to be ions, right? Because otherwise it's not possible. So that's why here it's asking you to list all predictable ions that are isoelectronic to argon. So we need to find all the so predictable, what does it mean here? So predictable means ions that you can predict from their position in the periodic table. So let's look at the periodic table. From the position of the periodic table, you can predict what will the alkali metals will do when they become ions. You will learn more about it in chapter 11, but when so alkali metals, they have what we call one valence electron, and they like to lose that one valence electron and be like the previous noble gas. So there will always be +1. Let me write this somewhere here. There will be +1 ions. Then next to them, the alkaline earth metals, they like to become 2+ ions because they have 2 valence electrons, and they like to lose them to be like the previous noble gas. So they lose 2 electrons and then become 2+ ions. That's the predictable ions. You cannot predict what the transition metal will become as far as when they become ions. Another one that you can predict are the group 3A, but only the metals. So, from aluminum, gallium, indium only actually. So these are group 3A, and they are predictable ions, and they become 3+ ions because they are still metals, right? And metal like to lose their valence electrons, and they like to lose there's 3 valence electrons to be like the previous noble gas. And then from the metals, that's the only one that are predictable. You know, in group 4A, 5A, the metals are not predictable in the sense that they don't make only one kind of positive ion. For example, a lead, here, lead, makes 2 plus or 4 plus ions. Bismuth, also 2 plus or 4 plus ions. Same with tin, 2 plus or 4 plus ions. So they are not predictable in the sense that they can make more than one kind of ions. All the ones we have seen up to now, like the alkali metal, will make always plus 1 ions. The alkali earth metals will always make 2 plus ions. And the aluminium, gallium, indium from group 3A always make 3 plus ions. Now on the non-metal side, so know that non-noble gases, you know, helium, neon, argon, krypton, xenon, radion, oganesson, they don't like to become ions because they are very stable. The name says noble gases, which means to be noble in chemistry means they are inert. They do not react. They like to be in the state they are in. And so they like to be just single atoms roaming around, you know, because they are gases, so they are roaming around free from each other, and they will not react easily. So they don't become ions. So then after that, the halogens, we know the halogens are fluorine, bromine, chlorine, iodine. They like to gain one electron because nonmetals like to gain electrons. They like to gain one electron and become negative one ions to be like the next noble gas. And then in group 6A, the oxygen, the sulfur, selenium, tellurium as well. You know, the non-metals here like to gain 2 electrons and be two negative ions to be like the next noble gas. And so on. You can also go here to group 5A. And here they like to become 3 negative ions because they like to gain 3 electrons to be like the next noble gas. So these are all the predictable ions. And I have a table below that shows them summarized here. So it's a very useful table here. Here it shows you how we have these predictable ions. The alkali metals with +1 charge, alkaline earth metals with 2 plus charge, 3A metals from 3A with 3 plus charge, and then the halogens or as -1 charge, and the groups of 6A with 2 negative charges. And you could add also the 5A with 3 negative charges. So these are what we call predictable ions because you know what kind of ion they become from their position in the periodic table. And they make only one kind of ion. That's the one you see that in there. The transition metals here form cations with various charges. They are variables, which means sometimes there will be 2 plus, 1 plus, 3 plus, 6 plus. They can have all kinds of charges, and depending on the element, it will be different. So these are not predictable. You cannot know from their position in the periodic table what kind of ion they will become. So let's go back to our question here, and it's asking to list all predictable ions that are isoelectronic to argon. I've positioned argon here. Argon is a noble gas in group 8A, and it's just to the right of chlorine. So argon has 18 electrons, but chlorine, when it's gaining an electron, so let's look at chlorine here. Chlorine, atomic number 17. It likes to gain 1 electron to be like argon and have 18 electrons. So chlorine is a predictable ion that is isoelectronic to argon. And I can go further here and look at sulfur. Sulfur, another predictable ion. Atomic number 16. Sulfur likes to gain 2 more electrons and have 18 like argon and become a -2 ion. So that's another predictable ion that is isoelectronic to argon. So these are the nonmetals, they form negative ions. But that's also the same with the metals. If you look at potassium, potassium atomic number 19, the element just after argon. It has 19 protons and 19 electrons when it's neutral. We just learned that potassium as an alkali metal likes to be a +1 ion and lose 1 electron and have 18 electrons only. So potassium with K+, when it's the K+ ion, is isoelectronic to argon. We can say the same with calcium. Oops. So calcium. Sorry. Calcium, atomic number 20. Calcium is an alkaline earth metal, likes to lose 2 electrons and have 18 electrons like argon. So again, that's going to be an isoelectronic ion to argon. And we can go even further here and look at gallium in group 3A. No. Hold on. I was going to say something wrong. So that's the isoelectronic ions, isoelectronic to argon. So let's go here and list them. And so we have the chloride ion, Cl-, the sulfide ion, S -2. The phosphide, oh yeah, that's on the other side. I could add the phosphide. The phosphide is also isoelectronic to argon. Let's look at phosphorus here. The phosphide ion, so phosphorus, atomic number 15, likes to gain 1, 2, 3 electrons to be like argon and have 18 electrons like argon. So that's also an ion that is predictable because it's always making a 3 negative ion. So phosphorus with 3 negative charges is isoelectronic to argon. So there is the phosphide ion as well, the potassium ion K+, and then the calcium ion Ca2+, are all isoelectronic to argon. So question 8, what is the formula of the ionic compound formed between sulfur and potassium? So sulfur and potassium. Let's start with potassium. Potassium, it's here, atomic number 19 in group 1A. So, and we just learned that potassium likes to lose 1 electron to be the +1 ion. So when the question is asking for an ionic compound, first I should say that ionic compounds are made of a metal, a cation that's from the metal, and an anion from the non-metal. So ionic compounds are made of a metal and a non-metal. Potassium is the metal and it will become the positive ion. And sulfur is the non-metal and will become the negative ion. So we already know now potassium is K+ when it's the ion because it's from group 1A. Sulfur, we just saw sulfur as well. And sulfur in group 6A likes to gain 2 electrons to be like argon. And so it likes to become a 2- ion. So that's sulfur likes to become the sulfide ion, right? So we have our two ion symbols, and these are predictable ions. So that's why you could find out their, charge from the position in the periodic table. When you want to write the formula between a cation and an anion, you always write the cation first and then the anion. And so here we will write K+ and then S2- next to each other. So there are two ways, if you, or maybe more ways to find the formula. There is the crisscross trick, or there is the fact that, and that's always true. To find the formula of an ionic compound, even though they are made of ions, you want the formula to be neutral overall, which means you want as many positive charges as you have negative charges. And here you can see an imbalance. There is one positive charge only from the potassium and two negative charges from the sulfur. So that means we will need two potassium K plus to cancel the charges on the sulfide. So notice how the charges for the ions are written in the upper right corner. So we will need two potassium K plus for one sulfide ion, so that all charges are cancelled. The two positive charges cancel the negative charges, the two negative charges. So that means you will need 2K and 1S. And so when we write the formulas, we write it like this: K2S, because you want two potassium. And so the two here will be a subscript after the K to say you need 2K. So the 2 belongs to potassium, not S. So it says here 2K for 1S, because the 1 are implied, we do not write them. So that's the formula for the ionic compound made between sulfur and potassium. The other way to do it is to use the crisscross trick. And let me show you how it looks when we do the crisscross trick. When you do the crisscross trick, you use arrows that will change. And maybe you should just make this bigger. Okay. Except that the arrows now are too small. So one arrow will go from the one of the plus charge of the potassium, and it will become a 1 subscript for the sulfur. So the charge number becomes a subscript for the other element. And the 2 from the two negative charges of the sulfur will become a subscript for the potassium. So that's why we say crisscross. The charge number becomes the subscript for the other element. So you see the 1 for the K plus here becomes a subscript of 1 for S, and then the 2 from the 2 minus of the sulfur becomes a 2 subscript for potassium. So that's how we can do this. Let's practice again with barium and chlorine. How do we find their formula? Again, barium is a metal and chlorine is a non-metal. So that's making together an ionic compound. So let's look at barium. Barium is atomic number 56 here. In group 2A, that's an alkaline earth metal. It's an alkaline earth metal, so it's a predictable ion. And we know it's making a 2+ ion. It likes to lose its 2 valence electrons to be like xenon. And the chlorine, the other one was chlorine. Chlorine is here. Let me clean up here. Chlorine, atomic number 17, is a non-metal from group 7A. And so it likes to gain 1 more electron to be like argon and become a Cl- ion. So that's the two. So barium is going to be 2+. And then chlorine is going to be Cl-. Let me make this bigger. Okay, so for now we have the two formulas for our ions. Or let's write the positive ion first, the negative ion second. You can do the crisscross trick, or you can see here that you will need another chloride because it's only 1 negative charge and there is 2 positive charges. So you will need another Cl- there to cancel the 2 negative charges, the 2 positive charges on the barium. And so you see that barium will have a subscript of 1 and chlorine will have a subscript of 2 by canceling all the charges, right? 2 negative charges here cancels the 2 positive charges. So we need 2 chlorine, and so there is a subscript of 2 for chlorine. And if you use the crisscross trick, you can see that as well. And let me show that here. So from the barium, you take the 2 of the 2 plus and it becomes a subscript for chlorine. And then the 1 from the negative charge of chlorine becomes a subscript for barium. And you get also BaCl2.